Good morning, all of you. We have been discussing about the most important topic in hydraulic machines part, hydraulic turbines. So we have finished two modules in hydraulic turbines. One related to the simple layout of a hydroelectric power station and various definitions related to the heads, efficiencies, and then classification of the turbines. In the second module in hydraulic machines, we discussed about the Pelton wheel, which is an impulse type high head turbine, the working of on the Pelton wheel, working proportions of the Pelton wheel, and velocity triangles for the Pelton wheel at inlet and outlet. Then the discharge equation, work done, and then efficiency condition for the maximum efficiency, and also the hydraulic design of the Pelton wheel turbine. Also, we have seen we worked out two problems relating to that. Today, we are discussing about the Francis turbine, modern Francis turbine. So this we already mentioned as an example in several cases while we were classifying the turbines. For example, with respect to the head, when we were classifying, we mentioned that the example for a medium head turbine is the modern Francis turbine. Similarly, based on the hydraulic action when the turbines are classified, we mentioned that modern Francis turbine belongs to the class of reaction type turbines. Pelton wheel, impulse type turbine, and this is a reaction type turbine where reaction pressure is responsible for the rotation of the turbine runner. Okay. Also, another classification that we made is about the mixed flow turbine based on the direction of a flow, where in the case of a modern Francis turbine, it is a mixed type flow turbine where the water is entering from the outer periphery, moves towards the center, and leaves axially at the center of the impeller or at the center of the runner. So this is what is called the modern Francis turbine. So today's class we concentrate on modern Francis turbine, its working in general about the reaction turbines, and in particular about the modern Francis turbine. Reaction turbine. One example is the modern Francis turbine, as I told you. So what are the various components of this modern Francis turbine? Their functions like scroll casing, spiral casing, steering, stay vane, their functions, guide ring, guide vanes and their functions, and a draft tube is provided. Why this draft tube is provided for these reaction type turbines or the modern Francis turbine in particular? Why not for the impulse type turbines? That also we will see. Then how the draft tube, where is it provided, and what is the advantages and functions of the draft tube, etc. we see. Then about the discharge of the turbine, work done, efficiencies, equations for the efficiency, working proportions, and the hydraulic design procedure for the Francis turbine runner, followed by one or two problems also we discuss. So in reaction turbines, water enters the wheel under pressure and allows over the curved blades. This is the first difference when you compare this with the impulse type turbine. In the case of impulse type turbine, at the exit of the nozzle, the water, the total energy gets converted into kinetic energy only, and hence there is no gauge pressure, or else it is under atmospheric pressure, it emerges out and strikes the buckets, and hence a Pelton wheel is called the atmospheric pressure turbine. Whereas in the case of a reaction turbine, water enters the wheel under pressure and flows over the curved blades. When the water flows over the curved blade, the pressure head is transformed into the velocity head. So there will be transformation of energy that takes place as the water is flowing over the surface of the vanes. In these turbines, water leaves the runner at atmospheric pressure. At the exit of the runner, it will open to atmosphere. But there will be a small issue if it is directly open to atmosphere. However, the difference of the pressure between the entrance and exit point is called the reaction pressure, and this reaction pressure is responsible for the motion of the runner, and hence these turbines are called the reaction turbines, sometimes called pressure turbines. One point that we need to understand from the figure is that the water may be entering maybe from the inlet, say from the penstock, and it moves over the periphery of the wheel and enters from the outer periphery towards the inside, and at the center it leaves in the axial direction. So this is the case of mixed flow turbine, where you have radial inflow towards the all through the outer periphery, moves towards the center, and from the center it leaves in the axial direction. You can see the arrows also, which are given very clearly, that blue and red arrows are given very clearly. So all through this scroll casing, the water flows. While it is flowing through this casing, the water enters in the radial direction towards the center, all through the periphery of the wheel, and leaves at the central portion in the axial direction, and this is called the mixed flow turbine. At the exit of the runner, you see, the exit of the runner, the pressure becomes atmospheric pressure. But the small issue is that if it is not open to atmosphere, the pressure can be contained, different from the outside atmospheric pressure, by connecting the exit of the runner to a draft tube. That is why the draft tube is necessary for this type of reaction type turbines. Whereas in impulse turbine, draft tube is not necessary. Why the draft tube is not necessary? Because it is a atmospheric pressure turbine. Either at the entrance or at the exit of the turbine runner, the pressure is only atmospheric in the case of impulse type turbine, and hence no draft tube is necessary. However, in the case of reaction turbines, when the water is entering under pressure, flowing over the vanes of the turbine runner, conversion of energy takes place. At the exit of the runner, it directly, if it is open to atmosphere, the pressure at the exit of the runner will be atmospheric pressure. The total head consists of partly pressure and partly velocity head. So you have both pressure head as well as kinetic energy, pressure energy as well as kinetic energy. Reaction turbines are classified as radial flow turbines, inward flow, outward flow, and mixed flow turbines. And we are looking at the modern Francis turbine, which is belonging to the class of this mixed flow turbine. Modern Francis turbine is one example of the reaction turbine. We have seen the reaction turbine, the difference between impulse and the reaction turbines. And we have noticed that at the exit of the runner, the pressure becomes atmospheric pressure, while at the entry of the turbine runner, we have the pressure, the liquid or the water enters with the pressure. As the water is flowing over the surface, energy transformation takes place, and hence the reaction pressure would be developed, and this reaction pressure is responsible for the rotation of the turbine runner. And modern Francis turbine is one example of the reaction turbines. Mixed flow turbine, and it is a mixed flow type of reaction turbine which operates under medium head, also requires medium quantity of water. When you take Pelton wheel, it works under a very high head, so the discharge requirement is very less, quantity of water required is less. Whereas in the case of modern Francis turbine, to develop the same amount of power, we need medium quantity. The discharge must be more than the Pelton wheel, because the head is less. The head at which the turbine works is only medium head, not the high head. So it works under medium head as well as the medium quantity of water. That means medium discharge. We know the power developed would be directly proportional to head and discharge. So if head is more, naturally even under low discharge condition, will be able to develop certain amount of power. On the other hand, when the discharge, when the head availability is getting reduced, naturally the discharge requirement becomes more to develop the same amount of power. So in this, water enters radially at the outer periphery, leaves axially at the center. You may see the construction of the reaction turbine. The outer thing which is now shown here is the casing. This is called a volute casing or a scroll casing. The central portion is the runner. At the center of the runner, a shaft is provided. So if you observe carefully, there will be two types of vanes which are connected over the periphery of this runner. There will be two types of vanes which are provided over the periphery of the runner. So the main components of a modern Francis turbine, if you see, there is a casing, also called the scroll casing or spiral casing, which will guide the water to move into the turbine runner in the radial direction, and a guiding mechanism. Then a main shaft for the turbine runner and the runner, and a draft tube which is provided at the exit of the runner. From the penstock, water enters the scroll casing. This is the first step. Water enters into the casing from the penstock, as it was done in the case of impulse type turbine. However, in the case of impulse type turbine, at the exit of the penstock, a nozzle is provided. Here, it is directly connected, and the water directly enters into the from the penstock into the casing under pressure. So this casing is called the spiral casing, also called the scroll casing, which completely surrounds the runner. We have seen in the figure also that the casing is completely surrounding the runner. So you can see here there are two types of vanes. One is the guide vane and the other is the stay vane. And and this is the entrance of the water into the scroll casing. So all this portion is the casing, and we have the runner. This runner is having two types of blades or vanes, guide vanes and stay vanes, and the central portion is connected to the shaft. Other end of the shaft is connected to the electric generator. So a pictorial representation of the Francis turbine runner is shown here. So these are all the vanes, the shape of the vane you can see here. These are all the curved vanes which are provided. These are the series of curved vanes which are provided here, and the flow takes place in the radial direction. So this is also another picture from the site where you have a runner which is connected with several number of blades or vanes. So this is the turbine installation in a hydroelectric power station. It's a mixed flow turbine which is provided. So the lowest figure, if you see here, I mean the small size figure, if you see here, all this is the casing. This casing, the round one, which is completely enclosed for the runner, is the casing. The shape of the casing is a scroll casing or a spiral casing, meaning that this is the entrance. This is the entrance of water. That means it is connected to the penstock. So from the penstock, the water enters into the casing and flows all through the periphery of the runner. While doing so, partly the amount of water is getting moved into the turbine runner in the radial direction. As such, along the flow direction, the amount of water, the discharge is getting reduced. If the discharge is getting reduced to maintain the constant velocity, A1 V1 is equal to A2 V2. So you need to reduce the cross-sectional area. That is the reason why a scroll casing is provided, a spiral casing with a gradual decrease in cross-sectional area along the flow direction around the periphery of the runner is provided. And what we have been discussing is about this draft tube. So what is this draft tube? This draft tube is connected to the exit of the runner. The central portion, the water leaves in the axial direction. So at this portion, this draft tube is provided. Usually, the draft tube would be with a gradual increase in cross-sectional area. The exit of this draft tube is connected to the tail race. So you have inlet and you have the outlet for the amount of water which is flowing. A small video representing about the working will be shown here. Okay, so there is a casing which is provided, and the purpose of this casing is to provide an even distribution of water around the circumference of the turbine runner. That is the reason why to have the constant velocity throughout the path of the flow of water around the circumference of the runner, we have the cross-section area of the casing which gradually decreases. So this type of casing is called the scroll casing or volute casing. And casing is usually made of a cast steel or concrete. From the casing, water passes through the speed ring, also called the stay ring. So this consists of upper and lower ring held together by series of vanes which are called the stay vanes. So from the scroll casing, the water enters directly into this stay ring. Usually the number of stay vanes will be half of the guide vanes. And from the scroll casing, water passes to the stay ring and vanes are called the stay vanes. The water coming out of this stay ring is made to pass through a series of guide vanes which are provided all around the periphery of the turbine runner. The function of these guide vanes is to regulate the quantity of water also to the runner, also to direct the flow of water, and to regulate the quantity of water. These guide vanes will be performing the function. You can see here the water entering here, all through moving through this scroll casing, entering all through the periphery of the runner, and then finally reaching towards the center, leaving at the center in the axial direction. The typical aerofoil shape may be like this, and the vanes are provided with this shape. This is called the aerofoil shape. The functions of the steering is it directs the water from the scroll casing. Also, it resists the load which is imposed on it. What do you mean by the load? The load is the demand. More power generation may be required at some point of time, less power generation may be required at some other point of time, depending on the demand of the power at the point of usage. So accordingly, the load on the turbine runner can be resisted by means of these stay rings, which are or stay vanes, which are provided. Then the guide vanes. So these are aerofoil shape to regulate the flow, and the water passing through this runner flows to the tail race through a draft tube. So draft tube, as we have seen in the figure, is a pipe of gradually increasing cross-sectional area, which is directly connected to the exit of the runner. Entrance of the runner to the exit of the runner, water flows, and at the exit of the runner, if it is left open to atmosphere, at the exit point of the runner, the pressure would become atmospheric pressure. To improve the efficiency of the turbine, to improve the working condition of these type of reaction turbines, at the exit of the runner, it is not left open to the atmosphere. Instead, a draft tube is connected, which will be directly connecting to the tail race. So this draft tube is made of a cast or a plate steel, sometimes concrete also. Okay, and it must be airtight. Please note that it must be airtight. Why it is required to be airtight is, if it is not airtight, inside the pressure becomes atmospheric pressure. Inside the pressure becomes atmospheric pressure. So in order to keep the pressure at the exit of the runner different from the outside atmospheric pressure, we should provide an airtight draft tube connecting the exit of the runner. In a small laboratory, probably you must have seen in our lab also, and probably you may see in the coming days, like this is a draft tube which is connected to the exit of the turbine runner. Okay, so this is the entrance of the turbine runner. Through this casing, the water flows all through the periphery, and from the center it leaves in the axial direction, directly connected to the draft tube. The exit of the draft tube is connected to the tail race. This is connected to the tail race. So in practice, if you see here how a draft tube is constructed, you can see. Usually the shape of the draft tube would be with a gradual increase in cross-sectional area. From the entrance of the tube to the exit of the tube, the cross-sectional area is gradually increased. The purpose is, if area is increased, once again apply the simple discharge equation, continuity equation. At section 1 at entrance, at section 2 at exit of the draft tube, A1 V1 is equal to A2 V2. So here the cross-sectional area is more. If the cross-sectional area is more, naturally the velocity will be reduced. That means velocity energy, kinetic energy is reduced. Total energy is constant, as we know, based on the Bernoulli's equation. So if the kinetic energy is reduced, the correspondingly it must have been converted into the useful pressure energy. Because it's a pressure turbine, we need to have the useful pressure energy there. That is the reason why at the exit of the turbine runner, to improve the efficiency of the runner, the draft tube is provided with a gradual increase in cross-sectional area. You can see here the cross-sectional area of the draft tube is gradually increased, and the exit of this runner, the exit of this draft tube is connected to the tail race. This is the tail race, and this is the inlet of the draft tube, and this is the outlet of the draft tube. The purpose of this providing the draft tube is it permits the negative pressure or the pressure which is less than the atmospheric pressure also can be there. That is called the negative pressure or suction head to be established at the runner exit, thus making it possible to install the turbine runner exactly above the tail race without having much of the loss of head. Without having much of the loss of head, we will be able to install the runner exactly above the tail race. Also, it converts large proportions of the velocity energy rejected from the runner into useful pressure energy. How it becomes useful pressure energy, we have seen that we are providing a draft tube which is with gradually increasing cross-sectional area. The angle of divergence of this draft tube should not be more than 8 degrees for the reason that the water flowing through the draft tube will not be in touch with the inner surface of the draft tube, thus reducing the efficiency. Suppose if the angle of divergence of a flow is more than 8 degrees, flow separation takes place. Because of the flow separation, the flow of water may not be directly touching the inner surface of the draft tube, leading to the reverse flow. Formation of eddies will take place. Efficiency of the draft tube will come down. Efficiency of the draft tube will come down. That is how, though you want to provide a gradually increase in cross-sectional area, the angle of divergence of this should not be more than 8 degrees. Similar theory you must have already seen in your venturimeter also. In your venturimeter, in the subject of fluid mechanics, you must have noted that there will be two cones for the venturimeter. The central portion is a throat, and there will be a convergent portion, there is a divergent portion. The divergent portion, the angle of divergence will not be kept more than 8 degrees there also, to avoid the flow separation and formation of eddies. Okay, so the sectional view of a Francis turbine is shown here, and the runner consists of a series of vanes which are fitted between the two circular plates. The runners are classified like a slow runner, medium runner, fast runner, depending on the speed of the runner. The runner may be cast in one piece or may be made of separate steel plates also, which are welded together. Either way, the runner can be prepared. They are made of cast iron for small output, cast steel for large output, and stainless steel when the water is chemically impure. You see, stainless steel, so naturally, if the water which is used for the generation of the power is not chemically sound, then we may use even stainless steel. The entire casing also. Okay, the runner also would be made stainless steel. Then that is all about the working. Then about the work done and efficiency. How do you calculate the work done and efficiency of a modern Francis turbine? Work done, we know in a general form, will be W by G into VWU plus or minus VW1 U1. Same notations I am using as was there in the impact of jets. Okay, VWU plus or minus VW1 U1. Okay, so work done per second is W by G, VWU minus, we have the different angles of beta, like beta less than 90 degrees, beta greater than 90 degrees, beta equal to 90 degrees. You have positive sign, negative sign, or VW1 being equal to 0. Particularly for the modern Francis turbine, the value of beta would be equal to 90 degrees because you have the radial flow there. So beta is 90 degrees. So if VW1 is equal to 0, then the work done per second would be W by G into VWU. Work done per second per unit weight of water, that this W will be taken to this side. Per unit weight of water, it will be VWU by G. And if H is the net head of the turbine, then the hydraulic efficiency will be equal to the work done per second per unit weight of water divided by the kinetic energy supplied per second per unit weight of water. So VWU divided by G whole divided by the input which is provided is the net head H. So VWU by G into H is the hydraulic efficiency. So if in case of any other type of reaction turbine other than modern Francis turbine, there is a possibility that the value of beta need not necessarily be equal to 90 degrees. Then you have the hydraulic efficiency VWU minus VW1 U1 by G into H, where the value of hydraulic efficiency may be between 85 to 95% for the value of beta being acute angle. Again, P represents the power developed by the runner shaft. Then the mechanical efficiency will be the power which is taken out, that means the power obtained divided by the power which has been produced. So W into VWU by G is the power produced and P the power obtained, the mechanical efficiency given by this expression. So power output divided by W by G into VWU plus or minus VW1 U1, in any case in a very generic form. If VW1 equal to 0 for a modern Francis turbine, then you have power output divided by W by G into VWU. Overall efficiency would be product of hydraulic, mechanical and volumetric efficiencies. Here, volumetric efficiency would not be there because you have a complete scroll casing and whatever is the water that is entering, all through will be allowed to flow through the periphery of the turbine runner and coming out. So there is no wastage of water, and hence the overall efficiency E would be equal to hydraulic efficiency multiplied by the mechanical efficiency. Usually the value of this overall efficiency may be varying between 80 to 90%. Then the working proportions for this Francis turbine. The ratio of width B of the wheel to the runner diameter D, width of the wheel to the diameter of the runner would be represented by N, which is called the breadth ratio. The breadth ratio, N is equal to B by D. The value of N may be usually ranging from 0.1 to 0.45 for the design considerations. The ratio of velocity of flow Vf at the tip of the vane to the theoretical velocity root 2 GH is called the flow ratio psi. Psi would be equal to Vf by root 2 GH, or the flow component of the velocity Vf would be equal to psi root 2 GH. The value of psi may be varying from 0.15 to 0.30. Then speed ratio Ku would be equal to tangential velocity divided by theoretical velocity, or U is equal to Ku root 2gh, as we have seen in the previous cases. Value of K may be varying from 0.6 to 0.99. So these are the three working proportions for the modern Francis turbine. One is the breadth ratio, N is equal to B by D. Suitably, it can be assumed between 0.1 to 0.45 for hydraulic design considerations. Second is the flow ratio, psi, which may be 0.15 to 0.30. Then the speed ratio, Ku, may be 0.6 to 0.9. Then how to carry out the design of this modern Francis turbine runner? So we know the design means what are the known values and what are the assumed values and what values that we are going to calculate from here. We are carrying out the hydraulic design. We are carrying out the hydraulic design for this turbine runner. So what is known and what are the parameters to be assumed and what can be found from this. Okay. So a Francis turbine runner is required to be designed to develop a known power P. We should be knowing how much power is required to be developed P when running at a known speed N, because this is from the generator consideration. For all these turbines, there is a shaft, one side turbine runner and the other side generator. So based on the generator consideration, the speed of the turbine runner will be fixed. The power will be how much power is required to be developed. Head is once again based on the water level available in the reservoir and height of the dam and level of the tail race. All these are the parameters based on which the head would be decided. So we know the values like the power required to be developed P, the speed at which the turbine runner is to be operated N, and the head of the net head available at the turbine runner. So P, N, H are the known values. We may have to assume the probable values like the hydraulic efficiency, overall efficiency, then the breadth ratio, speed ratio, flow ratio are required to be assumed. Eta H, eta naught, N, Ku and psi are required to be assumed. The ranges also are given appropriately. If it is not given, you may be taking the average of the given ranges. The design of the runner, which involves the determination of the size of the runner, that means how much diameter should be provided at inlet, outlet, breadth at inlet, outlet, and vane angles, alpha, theta, beta, and the value of phi. Of course, beta is 90 degrees for the modern Francis turbine. So this is to be computed. Step 1, determine the required discharge Q. P is equal to eta naught into gamma QH from the known value. Overall efficiency eta naught is equal to P by gamma QH. So from here, P is equal to eta naught gamma QH. So find the value of Q from there. What are the other parameters? P, power required to be developed, is known to us. Eta naught assumed appropriately between 80 to 90%. Gamma, unit weight of water, 9810 Newton per meter cube. And H is the head at which the turbine works, medium head. So H value also is known to us. What is not known from that equation is the discharge Q. Step 2, if Z is the number of vanes in the runner, T is the thickness of the vane at the inlet, and B is the width of the wheel at the inlet, then we have the total vane thickness which is blocked will be ZdB. Considering the effect of the vane thickness, the area of flow section would be pi dB minus ZtB. Please try to concentrate on this point again. What is this pi dB? D is the diameter. Pi d is what? It is a perimeter. Pi d is the perimeter multiplied by the breadth of the runner at inlet. The breadth of the runner at inlet provides you the entire area of a flow section, because in the case of a modern Francis turbine, the water enters all through the periphery of the turbine runner. All through the periphery of the turbine runner. Whereas in the case of impulse step turbine, there is a small jet provided. If d is the diameter of the jet, pi by 4 d square is the area multiplied by the velocity v gives you the total discharge coming out or entering into the turbine runner. But whereas in the case of a modern Francis turbine, the water enters all through the periphery. So you need to know how much the perimeter over which the water is flowing. If d is the diameter, pi d is the perimeter. And if b is the breadth of the runner, pi d into b is the total peripheral area through which the flow may be taking place. However, all through the periphery of the runner, water will not flow, because there is certain obstruction which is created by providing the vanes over the periphery of the runner. There are z number of vanes. Assume that there are z number of vanes which are provided all through the periphery of the runner. thickness of each vein is T, and all through the breadth of the runner they are provided. So T into B is the area blocked, area obstructed for the flow. There are Z number of such planes. So you have Z multiplied by T into B is the area which is blocked or obstructed all through the periphery of the runner. So the total peripheral area minus area blocked would give you the net area of flow through which the flow may be taking place. So pi dB minus ZTB is the area of the flow section. Pi dB minus ZTB. Then take pi dB as a common from both. You have 1 minus ZT by pi d, or this 1 minus ZT by pi d may be taken to be equal to K, which is known as the vein thickness factor. So K into pi into dB. The area available for flow will be K pi dB. Please note that K, vein thickness factor, which depends on the number of veins, which depends on the diameter, which depends on thickness of each vein. Then pi, of course, the constant. D is the diameter of the runner at inlet. B is the breadth of runner at outlet. Hence, the discharge would be equal to area of flow multiplied by velocity of the flow section, velocity of a flow. So K pi dB is the area multiplied by the velocity component Vf, flow component of the velocity Vf. So K pi dB into Vf is the discharge. Just now we have seen the breadth ratio N is equal to B by D. So substituting that, you have B is equal to ND square. So K pi into ND square into Vf gives you the discharge. In the step 1, you have computed what is the discharge. In the step 2, the discharge equation Q is equal to K pi ND square Vf. K pi ND square Vf. Now, step 3, the tangential velocity of the runner at inlet may be determined using the equation U is equal to pi dN by 60. U is equal to pi dN by 60. So it's all tangential velocity. So N is the speed in RPM, which is known to us. D is the inlet diameter. Just now we have computed from step 2. We have computed the value of D from step 2, and hence pi dN by 60 gives you the tangential velocity U at inlet. The velocity of will at the inlet of the runner can be determined using the hydraulic efficiency expression. Eta H is equal to VW by GH. We have seen just now in the definitions. So VWU by GH. Hydraulic efficiency may be assumed about 85 to 95%. And then what else is there? VW required to be computed. U you have computed from step 3. G acceleration due to gravity, and H is the net head. So you get the value of VW and you got the value of U. Both are known. Now draw the inlet velocity diagram. So from the inlet velocity diagram, you can see here, this is the inlet velocity diagram. V are the relative velocity and V is the absolute velocity. So the inlet velocity diagram is, you know the value of VW, you are the value of U. Okay, if alpha and theta are there, you will be able to compute the remaining velocities. How do you compute the remaining velocities? Take tan alpha is equal to Vf by Vw. Tan alpha is equal to Vf by Vw. Tan theta, Vf by Vw minus U. So from here, tan alpha is equal to Vf by Vw. Tan theta is equal to Vf divided by Vw minus U. So you will be able to compute the values of alpha and theta from here. Alpha and theta from here. Beta anyway is known. Now phi is required to be computed. The runner diameter D1 at the outlet varies about 1/3 D2, 2/3 D. You have capital D, the diameter of the runner at inlet. D1, the diameter of the runner at the exit or outlet. So this diameter can be computed as 1/3 to 2/3. 1/3 to 2/3. Average of half may be taken. 0.5 may be taken. So D1 would be equal to half of D. Accordingly, U1 would be equal to pi D1 N by 60. Here, pi dN N by 60 here, pi dN by 60. Now here, pi D1 N by 60. U1 is known. Now, based on the discharge equation, as we have already seen, Q will be equal to K pi dB Vf, which is also would be equal to K1 pi 1 D1 B1 Vf1. The suffix 1 represents that there are all the parameters at the outlet. I'm sorry, there is no pi 1, it is only pi. K1 pi D1 B1 Vf1. The suffix 1 represents that this is the parameter at the outlet. So usually it is assumed that the flow component of the velocity at the inlet is equal to that of outlet. Vf is constant. Vf is equal to constant, which means that Vf is equal to Vf1. and hence K is equal to K1. Also, B1 would be the breadth at the outlet would be twice that of the breadth in inlet. You see here what happened? If D is the diameter and B is the breadth at the inlet, D1 is the diameter at the outlet of the runner, which is half of the inlet diameter. Half of the inlet diameter. Whereas the breadth at the outlet is twice the inlet. Half of inlet here, twice the inlet here. That means diameter is reduced to half, the breadth is increased to double. Generally, the runner is designed to have the velocity of wheel VW1 at outlet being equal to 0. That means VW1 equal to 0. Beta is 90 degrees is the general design for the modern Francis turbine. And hence from the outlet velocity diagram, you can see here tan phi is equal to Vf1 by U1. U1 you already computed, pi d1 n by 60. U1 is known. Vf1 is assumed to be equal to Vf, and hence the value of phi can be computed. The value of phi can be computed. So what we have done is that known values we have taken, some values we have assumed, and we have computed the required values, which constitutes the hydraulic design of a modern Francis turbine. Known values are the head H, the power required to be developed P, and the speed of the runner. Assumed values are overall efficiency, eta naught, hydraulic efficiency, eta H, breadth ratio N, flow ratio, and speed ratio psi and Ku. Then computed values are capital D, the diameter of the runner at inlet, capital D1, the diameter of the runner at exit, then B, the breadth of the runner at inlet, the breadth of the runner at outlet B1, then vane angles alpha, theta, beta, and phi. If this is completed, then we say that it is the hydraulic design of the modern Francis turbine runner. Okay, so to compute the discharge, as we have already seen, discharge would be equal to area, Q is equal to area at inlet into velocity at entrance, or it is area at outlet into velocity at the exit. Meaning that whatever the quantity of water that is entering, same quantity of water is coming out. So A1 V1 is equal to A2 V2, where area at inlet is the area along the periphery of the runner from where the water enters the runner blade and is equal to pi into D into B, because all through the periphery the water is entering, so it is called the circumferential area or peripheral area. If D is the diameter, pi D is the perimeter, multiplied by the breadth, B gives you pi dB, which is the circumferential area at inlet. Circumferential area at inlet. So Q is equal to pi dB into Vf, where Vf is the velocity of flow component of the velocity at entrance. Similarly, at outlet, it will be Q is equal to pi d1 b1 Vf1. The discharge at inlet is equal to the discharge at outlet. If T is the thickness of one blade, Z is the number of blades, then the area blocked by the vanes will be Z multiplied by T into B, which is to be subtracted from the total circumferential area pi dB. Circumferential area pi dB. Thus, the net area through which the water flows at entrance will be pi d minus ZT into B. At exit, it is pi d1 minus ZT into B1. So these areas are sometimes taken as K pi dB and K1 pi d1 B1 respectively. So Q is equal to pi d minus ZT into B into Vf, all or pi d1 minus ZT into B1 into Vf1, which may be taken to be equal to K pi dB Vf or K pi d1 B1 Vf1. The work done by water per second on the runner would be W by G into VWU minus VW1 U1. As we have seen, beta being equal to 90 degrees, VW1 becomes 0 from the outlet velocity diagram, and hence it is only W by G into VWU. Okay, W, and then the work done will be W into VWU by G. In case for any other reaction turbine where the value of beta is less than 90 degrees, VW1 will be negative. So you have a very generic expression, VWU plus or minus VW1 U1 for the value of beta being less than 90 or the value of beta being greater than 90, VW1 with negative or positive values. We work out a small problem. Just I will be explaining this problem. You need to continue by going through this. Okay. So this data refers to a modern Francis turbine, and you have the head 50 meters. It is a medium Francis turbine. And in the classification we have given that a medium I mean, a medium headed turbine would be having a head range between 60 to 250 meters. I told you one more important point also at that point. These figures are indicative figures. You can't say that if the head is 59 meters, it becomes a low head turbine. So modern Francis turbine cannot be a medium head turbine. The problem is wrong. We can't say that. We cannot say that. The reason is the classification that is given is only to get the certain idea about what is high head, what is high, what do you mean by this high head, how high the head will be, what is medium head, what is low head. These figures are indicative. So in this present case, you have a modern Francis turbine, which is a reaction turbine, which is a medium head turbine with a head of 50 meters, speed 540 meters, output power 298.8 kilowatts. So what is given? H is given, speed N is given, output power P is given. P, H and N, three major things which are required to be given for the hydraulic design of the turbine runner are known. You need to assume certain values. Those values also are given here. Hydraulic efficiency eta H 95%, overall efficiency eta naught 85%, flow ratio psi 0.15, breadth ratio N 0.1, inner diameter of the runner 0.5 times outer diameter. That means D, capital D is equal to half of D1. Then 5% of the circumferential area is occupied by the vanes. What do you mean by this? 5% of the circumferential area is occupied by the vanes, which refers to the circumferential area pi into D into B. If you consider the area of blockage also, it becomes K pi D into B. K pi D into B, where K is referring to the vane thickness factor. So if 5% is occupied, the value of K would be 1 minus 5 by 100. 1 minus 5 by 100. So 1 minus 0.05, which is equal to 0.95 is the value of K in this problem. If it is not given, you assume 1.0. Assume 1.0. Then velocity of flow remains constant. What does it mean? The flow component of the velocity at inlet to the outlet Vf is equal to Vf1. Design the turbine. Design the turbine. So you have a runner blade, inlet, and inlet velocity diagram, outlet, and outlet velocity diagram with beta is equal to 90 degrees. With the beta is equal to 90 degrees. So what you need to compute here is that you need to go by the simple step-by-step procedure which is given there. In the design. Same procedure you need to follow. So inlet velocity diagram is given, outlet velocity diagram is given. Say head H is 50 meters, speed is 540, power is 298.8 kilowatts. Hydraulic efficiency, overall efficiency, and psi N and D1 is given to be equal to 0.5 times D, and K is equal to 1 minus 5 by 100.95, and Vf1 velocity of flow remains constant. Vf is equal to Vf1. So follow the step-by-step procedure. Vf is equal to psi root 2gh. Psi is already given, so compute the value of Vf. Eta H is Vw by gh. All things are known. All things are known here except Vw and U. So Vw into U is equal to 465. Also overall efficiency eta naught is equal to P by gamma QH. P by gamma QH. So known values you substitute here. Unknown value is the discharge Q, 0.705 meter cube per second. Q is equal to K pi dB Vf. Substitute all the values here. The value of D is not known. And get the value of D, 0.68 meters. D1 will be half of D, 0.34. Breadth ratio N is 0.1. N is 0.1. That means B by D is equal to 0.1 or B is equal to 0.1 into D. This is what has been substituted here. So value of B would be 0.1 into 0.68. So 0.068 meters or 6.8 centimeters. U is pi dn by 60, the tangential velocity, 19.71 meters per second. VW is already, we have computed 465, in which U is already known, 19.17. So VW is computed. Take inlet velocity diagram, take tan alpha, compute the value of alpha. Also tan theta, Vf by VW minus U, compute the value of theta. Take outlet velocity diagram, tan phi is equal to Vf1 by U1. U1 will be pi d1 n by 60, and hence the pi value is 26 degrees. So this constitutes the design. So what we have done now, the breadth B1, B. Similarly, the diameter D, D1, and the values theta, alpha, beta, and phi, which constitutes the hydraulic design of the modern Francis turbine runner. Okay, so this finishes the working of a reaction turbine, modern Francis turbine.